Hi everyone, my name is Mohammed Farhan and today I will talk about efficient maintenance of distance labeling for incremental updates in large dynamic graphs. This work is done in collaboration with Dr. Jing Wang. In this work, we studied the problem of shortest path distance queries in very large graphs. That is, given a graph G and any two vertices S and T to answer the shortest path distance between S and T in G. For example, in the graph shown here, the distance between 0 and 9 is 5. If such a graph is dynamically changing as a result of edge insertions, we can model this problem as dynamic shortest path distance query problem. As we can see in the graph given to the very right, the distance between 0 and 9 after inserting the edge between 2 and 5 is 3, but before it was 5. The dynamic shortest path distance query problem has many real-world applications. All of these applications are time sensitive. That is, they require distance in the order of milliseconds or microseconds. There are many approaches in literature that can be used to address this problem on dynamic graphs. The first one is search-based approaches, which require no update time but has a slow query time. The second one is labeling-based approaches, which guarantee a fast query time but are slow in updating the labeling and also have limited scalability. The next one is hybrid approaches, which combine labeling and online search in order to be able to answer distance queries on very large graphs with billions of vertices and edges. But still, these approaches have a very slow update time. So there is another way to guarantee an efficient update of labeling, that is to maintain the labeling. As we can see in this graph, only a very small percentage of vertices is affected as a result of a graph change, which means that if we construct a distance labeling from scratch, it not only wastes computer resources, but also prevent the availability of distance labeling for distance queries. There are few methods in the past that have been proposed to maintain a distance labeling, but these methods still have limited scalability and also take long time to update the labeling and has no minimality or do not preserve minimality. In this work, we consider highway labeling, which is a highly scalable approach, which has a very high scalability, which means this method can scale to answer distance queries on very large graphs with billions of vertices and edges, and also preserve the minimality of labeling. The problem with this method is that this only works on static graphs. We extend this method to dynamic graphs. A distance labeling is to compute a label for each vertex. For example, a label of a vertex is a pair of landmarks and distance to those landmarks from this vertex. As we can see in this graph, there are 3 landmarks, and to the right, the label of these vertices are shown, where the distance from vertex 2 to landmark 0 is 1, that is highlighted in red. A highway distance labeling contains a highway, which is a set of landmarks and the distance between those landmarks. As we can see in this figure, a graph with its highway is given. A highway cover labeling can be computed by giving a graph and a highway of that graph. As we can see here to the right, the highway cover labeling for the given graph and a highway. After computing a highway cover labeling, we can answer a distance query in 2 stages. The first stage is to compute the upper bound, and the second stage is to conduct a distance bounded search over a sparsified graph under that upper bound. A computing upper bound is to find a path of the minimal length through a highway edge. For example, in this graph, if we want to compute the upper bound between 3 and 9, we use the label of the vertex 3 and the label of vertex 9 and consider all the possible shortest path through the highway and take the minimum path. Then we conduct a bidirectional BFS on a sparsified graph. That is after removing the landmarks from the graph. As we can see, we conduct a bidirectional BFS on the graph shown to the very right. And this search yield a longer path that is longer than the upper bound. Therefore, upper bound is of the shortest path length, that is 4. When a graph is changed by an edge insertion or vertex insertion, then a query can result in our estimated distances. So there is a need to update the labeling as a result of a change. For example, here an edge between 2 and 5 is inserted. After the insertion of an edge, we can see the label of 5 and label of 9 are outdated. So there is a need to update the label of affected vertices that are highlighted in green as shown in the labeling. So for this purpose, we propose an incremental HL plus algorithm, which update the highway cover labeling in 2 steps. The first step is to find affected vertices, and the second step is to repair those affected vertices. So in order to find affected vertices, we conduct partial BFSs. For example, a partial BFS from vertex 5 with respect to landmark 0 is shown here. So we jump to vertex 5, which is the first affected vertex. Then from vertex 5, we find 3 vertices, 8, 9, 10 that are affected. And from those 3 vertices, we find 2 other vertices that are affected, 3 and 14. After finding all the affected vertices, we conduct partial BFSs to repair those affected vertices. During the repair process, we distinguish 2 types of vertices to improve efficiency. The first one is covered and the other one is uncovered. The covered vertices are those which has other landmarks in their shortest paths to the root landmark. Here, the partial BFS from vertex 5 with respect to the landmark 0 for repairing the labels of affected vertices is described below. Here we again start from vertex 5, we repair the label of vertex 5, that is add a distance entry of 0 in the label of 5 and move to 8, 9, and 10 other affected vertices. Here, vertex 8 is covered because landmark 4 is in the shortest path from 8 to 0. So we just remove the entry for 0 from the label of 8. And we repair the label of 9 and the label of 10 by adding the distance entry for 0 in their labels. Then we move to affected vertex 13 and vertex 14. And we can see that these vertices are covered because of the presence of landmarks in their shortest paths. So here red vertices denote the covered vertices from which we need to remove the entry from the labels, and blue vertices represent uncovered vertices for which we need to add or modify the entries. So we perform experiments using 12 large-scale real-world networks. We randomly sample 1,000 pairs of vertices in order to evaluate the average update time. We also randomly sample 100,000 pairs of vertices to evaluate query time of our method. First, we compare the efficiency of our method with the state-of-the-art method. As we can see, our method outperforms the state-of-the-art method in terms of update time. Next, we compare the performance with the state-of-the-art method incremental FD under varying landmarks. As we can see, our method outperforms on all the data sets with each selection of landmarks. And also we can see the performance gap is stable for most of the data sets. Next, we also test the scalability of our method by increasing the number of updates. We start with 500 updates and increase incrementally 500 updates up to 10,000 updates. We can also see that the update time of our method is far below the construction time of labeling on most of the data sets. The main contributions in this paper are we present an online incremental method that efficiently reflect incremental updates in billion scale graphs. Our method can also preserve minimality of high cover labeling, which helps in the improved query time. In future, we aim to work on decremental updates, which is also an important operation in dynamic graphs. We also plan to work on applying updates in batches instead of one by one. Lastly, we also aim to work on landmark selection strategies. Thank you very much.